We choose to go to the moon in this decade and do the other things, not because they are easy, but because they are hard.
I feel the liftoff. The clock has started. Roger. Godspeed, John Glenn.
Roger, 0G, and I feel fine.
This is a new and strange environment at first. Just suddenly finding yourself in orbit.
We have a liftoff, 32 minutes past the hour. Liftoff on Apollo 11. Houston, Tranquility Base here. The Eagle has landed.
Hello and welcome. This is Michael Annis, and you're listening to episode 20 of the Space Rocket History Podcast. And now, Tiros 1 and Echo 1, the first weather and communication satellites. In 650 BC, Babylonians began their study of the sky. In 350 BC, Aristotle wrote Meteorological. In 1592, Galileo invented the thermometer. In 1643, Torricelli invented the barometer. In 1870, telegraph technology facilitated coordinated weather observations. In 1900, at Galveston, Texas, a Category 4 hurricane claimed over 8,000 lives. In 1946, ENIAC, the first electronic general-purpose computer, began service. In 1950, ENIAC generated the first computerized weather forecast. In 1960, the first weather satellite was built. It was called Tiros 1. The Tiros program, which stands for Television Infrared Observation Satellite, was NASA's first experimental step to determine if satellites could be useful in the study of Earth. In 1960, the effectiveness of satellite observations was still unproven. Since satellites were a new technology, the Tiros program also tested various design issues for spacecraft, including instruments, data, and operational parameters. The goal was to improve satellite applications for Earth-bound decisions, such as, should we evacuate the coast because of the hurricane? Like so many things, Tiros was originally designed for a slightly different purpose. It began in 1957 as an Advanced Research Project Agency, that's ARPA, program to provide the Air Force with a high-resolution spy satellite. However, it was quickly determined that a television camera would not provide the high resolution necessary for military reconnaissance. But NASA believed its resolution was high enough to work for meteorology, and took over the project in 1959. Thus, the objectives of the Tiros program changed. Now the purpose was to demonstrate the feasibility and capability of observing the Earth's cloud cover and weather patterns from space, and to acquire information which weathermen could immediately use in an operational setting. Tiros also was used to test experimental television techniques designed to develop a worldwide weather satellite information system, and to a lesser extent, test sun angle and horizon sensor systems for spacecraft orientation. Here's a news clip describing the satellite.
Tiros, meaning Television and Infrared Observation Satellite, is more than just a dream. This experimental weather satellite means that man's vision is no longer limited to looking up at the clouds gathering above him. The eyes of the satellite are two television cameras, one with a wide angle and one with a narrow angle lens. A series of individual pictures can be transmitted directly to Tiros ground stations, or the pictures can be stored on two videotape recorders in the satellite.
Tiros 1 was 42 inches in diameter, 19 inches high, and weighed 270 pounds. The satellite was made of aluminum alloy and stainless steel, covered by 9,200 solar cells. The solar cells served to charge the nickel-cadmium batteries. 3 pair of solid propellant spin rockets were mounted on the base plate. Tiros had 2 television cameras, one low resolution and one high resolution. A magnetic tape recorder for each camera was included for storing photographs while the satellite was out of range of the ground station network. The antennas consisted of 4 rods from the base plate to serve as transmitters and 1 vertical rod from the center of the top plate to serve as a receiver. The craft was spin-stabilized and space-oriented, not Earth-oriented. This meant the cameras could only be operated while they were pointing at the Earth when that portion of the Earth was in sunlight. The launch vehicle was a Thor Able, which you may remember from episode 14, consisted of a Thor first stage and a second and third stages of the Vanguard launch vehicle. The Thor Able stood 90 feet tall, and the diameter at the base was 8 feet. It was liquid-fueled and capable of delivering 150,000 pounds of thrust. The second stage was also liquid-fueled. It could deliver 7,500 pounds of thrust, and the third stage was solid-fueled, and it delivered 2,760 pounds of thrust. Tiros 1 was launched on the first try on April 1, 1960 at Cape Canaveral. It was inserted into a low Earth orbit. The wide-angle cameras provided views that were approximately 750 miles wide, and the narrow-angle camera provided views that were about 80 miles wide. There were 2 command and data acquisition stations. One was located at the Army Signal Corps Laboratory in Belmar, New Jersey, and the other was a U.S. Air Force facility at Kainea Point, Hawaii. When the satellite was within range of a ground station, the cameras could be commanded to take a picture every 10 or every 30 seconds. But each camera was also connected to a clock-controlled tape recorder to record images when the satellite was beyond the range. Each recorder contained 400 feet of tape and could record up to 32 pictures for playback the next time the satellite was within range. For 2.5 months, Tiros 1 performed admirably, returning almost 23,000 black and white images from its 2 cameras. However, on June 15, 1960, Tiros suffered an electrical systems failure which ended the usefulness of the satellite. Unfortunately, it did not last long enough to help during hurricane season, and weathermen missed its photos when Hurricane Donna headed up the East Coast. Furthermore, Tiros 1 was in a low Earth orbit, so it could not provide views of the entire hemisphere. Most modern weather satellites are in geosynchronous orbit 22,300 miles up, so that they stay in a stationary position over the Earth because their orbital velocity matches the rotation of the Earth. This orbit allows them to provide panoramic views of the entire hemisphere. Tiros 1 was operational for only 78 days, but it proved that satellites could be a useful tool for surveying global weather conditions from space. Additionally, Tiros' test of experimental television techniques led to a worldwide meteorological satellite information system. It also was the first satellite to test sun angle and horizon sensor systems for spacecraft orientation. Tiros 1 provided a vast improvement over the use of aircraft to track severe storms, and unlike planes, it couldn't be grounded in bad weather. In 1939, George W. Mindling, a Weather Bureau official in Atlanta, Georgia, wrote prophetic lines as part of a group of weatherman poems. Here's an excerpt from his poem. Who can say what contraption the future will bring? There can be not a doubt some more wonderful thing. And if anyone ventures the future to scan, why indeed should it not be your old weatherman? Have you noticed how often in times that are past we have used new inventions to improve the forecast? Television is coming, it's not far away. We'll be using that too in a not distant day. Photographs will be made by the infrared light that will show us the clouds both day and by night. From an altitude high in the clear stratosphere will come pictures of storms raging far, if not near, revealing in detail across many states the conditions of weather affecting our fates. 21 years later, George Mindling's prophetic poem ceased to be prophecy and became a fact, with the launching of Tiros 1 on April 1, 1960. The first true communications satellite also went up in 1960. The idea for communication satellites gained credibility in 1945 when science fiction writer Arthur C. Clarke hypothesized that 3 satellites placed in geosynchronous orbit 22,300 miles above the equator could be used to bounce radio waves around the globe. The idea thrilled many scientists, and with the dawning of the space age, NASA began an effort to make it a reality. The principle behind a communication satellite is simple. Send the signal into space and send it back down to another spot on the globe. NASA engineers soon discovered the easiest way to accomplish this was to bounce signals off a giant metal balloon floating in orbit. The concept was developed into the aptly named ECHO program. As a side note, similarly to Tiros 1, the original idea for putting a balloon in space was for an entirely different purpose. A NACA engineer, William O'Sullivan, had conceived it as a satellite that would measure density at the limit of the atmosphere by experiencing drag. However, John Pierce, director of communication research at Bell Labs, thought of a different use. He believed he could bounce a radio signal off of it and have the signal received on the other side of the country. Thus, ECHO 1. The ECHO 1 spacecraft was a 100-foot diameter balloon made of aluminized mylar polyester film, about a half a mil thick. The balloon satellite functioned as a reflector, not a transceiver, so that after it was placed in low Earth orbit, a signal would be sent to it and then reflected off its surface and returned to Earth. Because of the large area-to-mass ratio of the spacecraft, data for calculations of atmospheric density and solar pressure could be acquired as well. ECHO 1 was equipped with beacon transmitters for telemetry purposes. These transmitters were powered by 5 nickel-cadmium batteries that were charged by 70 solar cells mounted on the balloon. The spacecraft was nicknamed Sataloon by those involved in the project because it was a combination of a satellite and a balloon. The entire satellite weighed about 400 pounds. The launch vehicle was a Delta, which was similar to the Thor Able that launched Tiros. Delta rockets were an amalgamation of 3 smaller boosters. The first stage was a modified Thor intermediate range ballistic missile with a modified Able second stage topped with an Altair rocket. The configuration could launch 650 pounds into a low Earth orbit. The first launch attempt for ECHO 1 was made on May 13, 1960. Unfortunately, it ended in a catastrophic failure when the second stage attitude control system malfunctioned. The next attempt was made on August 12th. Here's the audio clip.
Mode control switches.
Less than a minute remains in the countdown.
13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0.
As the missile hurtles through space, the control center maintains communication with it, checks its position, and automatically sends any necessary steering orders to keep it on its predetermined path. This guidance system was designed by Bell scientists, the same system that meets the precise target demands of the Titan intercontinental ballistic missile. Its job here is to put the ECHO satellite in orbit with pinpoint accuracy. Will it? That is the question these men ask themselves as they finish monitoring the guided portion of the missile's flight. And will the balloon, squeezed into a 26-inch sphere, release okay? Will it inflate properly or burst into fragments? They still have to wait. High in the sky, the third stage burns out. The payload section separates from the engine. the protective shell springs apart, releasing the balloon. Floating clear, the balloon is inflated by a chemical powder which instantly vaporizes in the vacuum of outer space. The men won't know it for some time yet, but balloon inflated and in orbit. As the minutes pass.
As you heard, Echo 1 was successfully inserted into a 944 by 1,048 mile orbit. Next came the inflation of the balloon. During ground test, 40,000 pounds of air was needed to fill the 150-pound balloon, but in the vacuum of space, it only took a few pounds of gas to fill the sphere. Here's a news report on the success and the first communications test.
Closely following the recovery of the Discoverer capsule at Cape Canaveral, another historic satellite is ready for launching. In this nose cone is packed the 100-foot balloon of Echo 1 to be carried into orbit by a Thor-able Delta rocket. It's only the second firing of this three-stage missile, but the 92-foot rocket performs flawlessly. This launching, closely followed by successful tests of Atlas and Polaris rockets, was a landmark in America's spectacular two-day display of progress in space research. Once aloft, the inflatable balloon satellite, the height of a 10-story building, immediately proved its worth by bouncing from its surface a recorded talk by the President from New Jersey to California. The radio mirror satellite, as bright in the northern sky as the brightest star, reflected Ike's recorded talk with impressive clarity and fidelity. In itself a major feat of America's spacemen, Echo 1 foreshadows a new era in global communications when a chain of sister satellites will closely link all parts of the globe.
And here is Eisenhower's transcontinental speech transmitted from New Jersey, reflected off Echo 1 and received in California.
This is President Eisenhower speaking. It is a great personal satisfaction to participate in this first experiment in communications involving the use of the satellite balloon known as Echo. This is one more significant step in the United States program of space research and exploration. The program is being carried forward vigorously by the United States for peaceful purposes for the benefit of all mankind. The satellite balloon, which has reflected these words, may be used freely by any nation for similar experiments in its own interest. Information necessary to prepare for such participation was widely distributed some weeks ago. The United States will continue to make freely available to the world the scientific information acquired from this and other experiments in its program of space exploration.
As you can imagine, it would be difficult to keep a balloon inflated in space due to the meteorite punctures and skin permeability. NASA used a make-up gas system of evaporating liquid or crystals of a subliming solid to produce the gas needed to keep the balloon inflated. For several weeks, ground stations experimented with the sphere by bouncing signals from one station on the Earth to another, and it was successful. It worked between points in America, and it worked transatlantically as well. The satellite's shiny surface was also reflective in the range of visible light. Echo 1 was easily seen from the ground with the unaided eye as it passed over the Earth. During the latter portion of its life, Echo 1 was used to evaluate the technical feasibility of satellite triangulation. Spacecraft survived in space until May 24, 1968, when it re-entered the Earth's atmosphere. Since Bell Labs was a part of AT&T, this was the first satellite to serve the needs of private industry. It represented the first important move toward commercial enterprise in space. And satellite communications would become the predominant use of space for the world at large. Thanks for listening to this archive episode of the Space Rocket History Podcast. If you are financially able, please support the podcast by going to the homepage, spacerockethistory.com, and clicking on the orange Donate button or the Patreon link. Thanks.